Let me introduce our first speaker for today, Brian Beres, who will be discussing drought mitigation strategies for crops. So Brian is a senior research scientist at Agriculture and Agri-Food Canada's Lethbridge Research and Development Center. So welcome, Brian.
Yeah, thanks for having me, Matt. So thanks again to Matthew for inviting me to speak here today, hosted by County of Lethbridge, my old stomping grounds. I grew up on a farm right across the road from Ready Made School, for those of you that are tuning in from nearby. So it's nice to, in a way, come full circle back to Lethbridge County. Um, so Matt asked me to talk a little bit about this. So what I thought I'd do is start off a little bit globally and then narrow down right down to basically Lethbridge and what we're doing at our site with some examples. But what I think is important when we talk about things like heat and drought stress is learning from other areas or getting an appreciation for what they're going through. And Australia is certainly one of those. But there's other regions as well in the US and the Great Plains there. So it's it's been a real pleasure to work with colleagues from Australia like John Kirkgard. And then I teamed up with some folks from the University of Nebraska and Kansas State University, Patricio Grassini and Romulo Lalato and GZ Wang. He's a biologist working on my program. So thanks to those guys for sharing some slides or contributing to this. And so what I thought I would do is just talk a little bit about, getting a bit realistic about what our yield potential is and how to exploit and close down a yield gap if that's the thing that you have, and kind of always hitting, if you've heard me talk before, this context of we really need a more systems approach. And sometimes we get stuck in silos, or we get too focused on varieties, or we get too focused on management practices. And the reality is we need to sort of think about it in a systems approach. So the proper system and synergy that you can get when you properly combine things like genetics and management to overcome or exploit a certain environment, that's the key. And so that's kind of what I'll be trying to hit home today in the context of I suppose, drought management. So prairie wide, this was a review paper that was just recently published, and I kind of highlighted it because I was a editor-in-chief for the Canadian Journal of Plant Science, so I've made it actually one of my editor choices for the year. But basically, they just looked at climate change trends on the prairies, and so what I sort of keyed in on some things that I think are to our advantage potentially. And basically, long story short, is we're going to increase by about 3 weeks our frost-free period, combined with also an increase in growing degree days. So that to me is something we could possibly exploit on the prairies. One thing of concern, of course, is that we have decreased off-season precipitation. And as you can see, as I'm talking on January 27th, it's 5 degrees outside and the snow comes and goes real quick. And so that snow cover duration is something that's been dropping. That's not good. And then I think, if we think and we appreciate that these trends are real, the status quo isn't going to cut it, especially in the context of drought management. And so, for example, the conventional thinking we've been doing, and I'll talk quite a bit about this too, is this project called ultra early seeding, where basically we're telling producers to abandon seeding by calendar dates and strictly go by soil temperature, no matter when that happens. But as you can see, this is something I pulled off Twitter, somebody locally saying, oh, chill out, you don't have to seed early. And they're quoting the preferred temperature to plant is 20 degrees. So that's the conventional thinking, which I would argue, if we need to change, probably is something we need to address. So anyway, a little bit about just what our yield gap is and what's possible. And I think sometimes we forget where we are in the northerly latitudes. Saskatoon, for example, I think is almost directly on the same latitude as Siberia. So we have to sort of temper expectations. Um, but anyway, what is ultimate yield potential? Well, on your farm, it's going to be a combination of things like radiation, temperature, amount of carbon dioxide, and the genetics that you're using. And it's all ultimately driven too by water supply and the soil type and texture that you have. So that's what's possible based on your environment. And so what we try to do is take a look at that and compare it to what you're actually getting for yield. So this average yield, um, as a consequences of nutrient management, planting strategies, other integrated pest management. And so what does that look like? And so theoretically, if it's, hypothetically, if it's here, um, this is what we call the exploitable yield gap. Now, notice that we're not saying to take the gap right to 100%. What we're saying is um, you probably want to be within more like 80% of yield gap closure. That other 20% to close that down would be cost prohibitive, more than likely. And so we mapped that out for the prairies, Patricio Grassini, myself, Romulo Lalato, and this is what it looks like. So if you take sort of, we're in this darker orange here where we are in darker orange, 4 to 4.8 tons per hectare. So that's right around 75 bushels, I would say, per acre on dry land is basically what our potential is. And that's not to say some guys aren't exceeding it. It's just on average, when you average it over, that's what we're potential rests around there, which ironically or interestingly is a bit better than what you see down in the States. And then how does our yield gap closure compare? Well, it's not bad. This turquoisey color here suggests that we're in that neighborhood of 60 to 70% on average. And, so we've got work to do, but, if we say 80s is the max we want to go anyway, I mean, we're close, but, this should, I think, give us a good idea of what to target for research priorities and what's important, what's possibly lacking on your farm. And this is an interesting example that popped up on Twitter last week where, you always hear about these yield contests. So somebody on 20 acres just has these ginormous yields, right? So this grower out of Saskatchewan, Stuart Lawrence, he kind of put it in perspective. You would have to have a break-even yield of 180 bushels per acre to meet or pay for those input costs that resulted in the type of yields that these guys were getting here in New Zealand. So again, tempering expectations is key, I think, particularly depending on what's going to happen with this year, both with climate, tariffs, and what other nonsense potentially is something you experience on farm in the way of getting in the way of your profit margin. And so what are some practices for us that are important, and what are we actually trying to accomplish? What are we trying to change when we talk about drought management or yield potential or what have you? And this is kind of the conventional thinking. So this is something by Gustavo Slafer, who I've gotten to know a little bit. He's a really well-known physiologist, and this was a review paper that they published recently with basically a new hypothesis of how to think about yield and what affects yield. And so he's saying, we've kind of focused a lot on the duration of the growing season. If we can stretch that out as much as possible, that's a good thing. And what he's saying is, yeah, okay, that's potentially important, but what's more important within that growing cycle is what's called the critical growth period. And basically that's from stem jointing all the way up and past like 10 days post anthesis. So this is the critical piece here. And this is why you can have your crop get beat up, your cereal crop, with hail, or you decide to graze it or whatever, and you really don't impact yield. But you get inside this critical growth period, and that crop starts having and experiencing stress, that's going to directly impact your yield. And the other the other piece to go with that is this source strength. Without diving into the weeds of source sink relationships and physiology, basically you've got to have your management practices dialed in and all those resources available to that plant by the time it hits the critical growth period. So think about your nitrogen management or your nutrient management or your weed control. If you don't have weed control managed in time, that this becomes stress because of competition or a lack of nutrients, you're going to throw away yield. So critical growth period, that's what we're talking about, and that's what we're going to try and change a bit. And he gives two really good examples too about, so here's the critical growth period here, these little arrows here. And what we're trying to do is stretch that like a rubber band. We want that critical growth period to be as long as possible because that's going to translate into higher yields. And it's also a reason why even here winter wheats can yield more. It's because of not just how we plant it and it's a winter growth habit, but the winter wheat tends to have a longer critical growth period because that plant has completed its that critical growth period stage before, the heat and drought stress that you get here in July and August. And anything over 30 degrees, if that wheat crop or whatever is still flowering, it's going to abort those flowers and you're going to have less seed set. So really important to keep in mind the critical growth period and stretch it like a rubber band as much as we can. And the reason, Northern Hemisphere winter wheat, especially UK, they can get 9-10 tons per acre. Same with spring wheat down in southern Chiles. They get the radiation, going back to our yield potential talk, but they don't experience that heat and drought stress that we get on the prairies. And so they're able to enjoy those types of yields that I would argue aren't really possible with our short season, our northerly latitudes, etc. And so kind of with that in mind, and I sort of came up with this concept of forgetting about when we can plant according to a calendar and instead thinking about, okay, what is really possible. And we all saw opportunities. I'm not the person to come up with the idea that you could get out into a field in March, for example, but there was a certain aversion to that because of a perceived risk. Why would I plant that early? Because those plants are going to suffer and die more often than not, even if I could get in there. So we developed this study and got the funding, and we started in about 2015 in the field. And this is Stephen and Warren here. And basically it's a prescriptive practice. You get yourself a soil temperature probe, doesn't have to be anything fancy, stick it in 2 inches in what you read. And if it's basically over 0, you're ready to plant wheat, is what we've come up with after about 50 site years of data. But when we first started, we didn't know what that sweet spot would be. So we would start at 0 and go in increments of 2 degrees up to 10 degrees. And think back to that tweet earlier that I showed where 10 degrees was where that person said was the sweet spot to be waiting. Wait until 10 and then go plant. So 10 conventional, 0 basically insane is kind of what conventional thinking was. But we were able to plant in that first project as early as February 16th. And then with a follow-up study, after we've proven quite conclusively that you can go in, and the sweet spot ended up being 2 degrees for spring wheat. We then started some additional work around Durham and whatnot, and the earliest that we've gotten in is February 9th. So that's when we first read 0. And so I don't think there's too many people even in Lethbridge County thinking I should go plant spring wheat in February. But if it's a prescriptive practice and you're committed to it, once you read that, that's your trigger, as we call it, to go plant. So that's a really important, I think, thing and a challenge to accept, I think, given the conventional and cultural norms around planting, and that, 10 degrees and over is really where I should be planting. And on top of that, and if you look at the conditions here with Stephen planting here, February 9th, I mean, does that look like February 9th? No, it looks like mid-April, but that's when we could go. And this is a drill that we built ourselves. But it's got the pillar lasers discs, and it works great, and it was very successful. But in Lethbridge County, I think in Ready Made, I think the cutoff for cereals is May 10th. So I think people just thought, well, there's no yield penalty provided I'm in by May 10th. And what we're saying is, no, we're not saying you're going to get a great yield bump with this practice, but you're definitely going to have greater yield stability. You'll never lose out on yield, rarely. And why does it work? Well, think back to that critical growth period. Basically, if you plant conventionally, even in the end of April, you're going to have a big part of that critical growth period, which is in red here, in July. But with convention or with ultra early seeding, we literally shift that entirely out of July. So we're not going to get those 30 and above temperatures hitting our crop when it's vulnerable. And in fact, this past year, we harvested August 1st some of our durum, and I'll show you that in a little bit. And basically, what we learned from this is, from our sort of sweet spot of 0 to 3 degrees, every increment of and delay of waiting for those soils to warm up results in a yield drag potentially. And it's a double whammy if you go with a lower seeding rate. So for us, we're recommending with spring wheat 400 seeds per square meter or 40 seeds per square foot. But if you cut that in half, which is pretty common, you just can never catch up. And in fact, that starts to widen as you delay your planting. And we've had a lot of success with uptake of growers and their experiences. Seldom, actually, I've yet to hear of a negative outcome. Fellows like Matt Gold up in central Alberta, this isn't just a southern Alberta thing. We've been as far north as Dawson Creek, all over Alberta and Saskatchewan. He's planting his spring wheat and there's still snowbanks in the tree line, but it ends up being the best crop he's ever had. So that's the experience. And again, locally here, so this was just this past summer. And here's that sweet spot treatment. We planted this 0 to 3 degrees in that range. So as soon as it was basically over 0, the guys were in there planting. And there's the sample from August 1st. So we were able to complete the harvest much earlier, and there was no negative consequence for doing it. You're out of the field earlier, and potentially you're getting higher yield as well. And this is why there's probably concern about doing it. Every time we do this, sure enough, you're going to end up with snow and cold weather after you plant. And this is when we planted February 9th, and you saw what nice conditions we had for planting that. Well, on April 12th, we had a snowstorm, and the seedlings were actually up. And you'd look at that and think, well, those seedlings are going to freeze. They're in big trouble. And the reality is, by virtue of where we're breeding, it's never an issue. And you can see here from this year's sample, there's that treatment right there. Stevens combining it there. CDC Defy, highest yielding treatment was when we planted at the sweet spot. So in this case, we were getting not just intangible benefits, but we were getting an actual yield increase by going ultra early as opposed to waiting to that 10 degrees. And the trend pretty much was the same with our other two varieties as well. And interestingly, we started this other project where I was interested in now comparing that to winter wheat in a nitrogen management context and a greenhouse gas emission context. But for today, kind of interesting to see where those are. So this is AC Wildfire, one of the latest from the Lethbridge Winter Wheat Breeding Program. This is AC Brandon, came out about the same time as Wildfire. And then this is Brandon if we waited to that 10 degrees and planted, 8 to 10 degrees and planted. So again, we suffered a yield penalty by waiting and planting at the conventional time. with all of this. And it's more notable, I would say, in a rain-fed context, dryland context. You can see here a big yield decrease by waiting, whereas if moisture isn't a limiting factor, waiting tends to help, be as successful. But if there's tremendous risk in a dryland situation to wait for water, and I think this is the price you pay if you're going to try and do that. That's not to say it'll never pay off, but I would argue it pays off maybe 1 and 2 years out of 10, whereas ultra early pays off probably 7 to 8 minimum out of 10. And here's an example of that. So this is a different study with spring wheat this past year. And you can see here this top line is 2024. And you can see going in at 0 gave us way better yield than waiting until 10 degrees here. But there are years, there was one in fact where, let's see, which year is this? It looks like 21, where it was super dry. And if you waited, you may have gotten a bit of a yield bump, maybe. And then there are years when, it just doesn't matter. And that goes back to the critical growth period. If you have really, really severe drought and heat stress, when you plant really won't matter. Everything will shrink down. So that rubber band's going to shrink down. And, at that yield level, which isn't very good, like 15 bushels an acre or something, it just didn't matter. But when yield goes up, the thing to keep in mind that the practice of ultra early seeding seems to become more important. And this is just a quick example of what's potentially happening on the prairies with respect to, if you don't seed ultra early and you're waiting and you're going to expose your crop to July and those plus 30 degree days, those days over time are going to increase according to this modeling here. This is basically what that's showing. And, where we are isn't too bad. A practice of ultra early seeding, I would argue, kind of mitigates against that. But you get into, 20, 30, 40, 50 days of that, it's going to take considerable change in practices and whatnot to overcome that. So in terms of what we learned, we found that our sweet spot is probably, 2 degrees, 0 to 3 degrees, that kind of thing, if the field permits that you can get in there. The higher seeding rate was important, like I showed. Seed treatments haven't been that important at Lethbridge anyway. They sure are important in a winter wheat context, but we didn't really seem to see much of a response at Lethbridge for that. And then the big thing to keep in mind right here in Lethbridge, I kind of used ready-made as an example. Like if you seeded at a conventional time and you went with that lower plant population versus going at 0 to 3 degrees or whatever and going with that higher seeding rate, you left about $200 a hectare on the table, according to our math. And you can question my math all you want, but I would still stand firm that you're leaving money on the table. And if you think we've got a problem with moisture, look at some of the stuff happening in Australia. And so, ironically, what's going on there is it's similar but a little bit different. Here, it's really hard to get winter wheat acreage stable in high numbers for a lot of different reasons. But in Australia, they're actually switching to it because what they found is their rainfall patterns have changed so much. The tap pretty much just turns off, and it's no longer in areas possible to really have success with spring wheat. So they switched and they're moving into not just winter wheat, but they're looking at all sorts of interesting practices, earlier plantings, and same thing, they're showing penalties if you're delaying it. But they're also looking at all sorts of things there where I think we're a little bit behind, frankly, in Canada with where we're taking some of our physiology and breeding priorities. For instance, they're looking at fast winter wheat. So back to that critical growth period, trying to shorten that down as much as they can without losing yield and trying to gain yield from that. So that to me is pretty interesting. And also, I think I jumped one here. Just hang on. No, that's it. They're all. Oh yeah, it's later on. So anyway, that's kind of in a nutshell. So it's not just what we're doing here. It's kind of a global, obviously, concern, the whole heat and drought stress thing. And so then, okay, now what about this in the context of managing nitrogen? Just quickly here. And going back to that same paper, Gustavo kind of showed that, I don't know what you guys are doing on your farm particularly, but back to that critical growth period, the most success they had was actually banding all their nitrogen at planting. And we recently looked at something like that where we were also comparing nitrification inhibitors, urease inhibitors, polymer coated urea, comparing that to just straight urea at different banding or timing and placement strategies, all at planting, a split application, a triple split, and so on. And for you, I think it boils down to economics. And don't forget, in a dryland situation with spring wheat, we can rarely show any sort of improvement beyond 120 kilograms of nitrogen as a rate. So keep that in mind, because I know there are farmers, particularly in Manitoba, that are pushing to 180, and I don't know that they're really reaping the benefit they think they are. Now, when it comes to urease inhibitors, and particularly in a dryland situation, this was one of our plots recently. I'm sure some of you can relate to in the past 3-4 years. Here's urea as net returns in the Lethbridge area. But you can see these urease inhibitors and other sources are actually paying for themselves. So I wouldn't poo-poo on the idea of adopting a urease inhibitor. What we've seen actually also is that you can improve your yield stability. And I think what we've also learned with a nitrification inhibitor is it's even better because you have both in the case of a dual, you have both a nitrification inhibitor and a urease inhibitor. Now you pay a bit more for it, but the reality is you can get back a lot more too in certain situations. Interestingly, on the economic side, all banding paid, at least numerically, a little bit better. Our triple split was not successful. That's probably our fault with how we were managing that triple split. But 2 splits was the same as all banded. So if you're into splitting, great. If you're not, that's okay too. And this is kind of an example of that. This looks more complicated than it is, but basically these are F values from an ANOVA. And so when we see big numbers or big F values, we're interested in what was going on there. So here's one, for example, which one did I want to show? That's a pretty good one here. So high productivity area, 7+ tons per hectare. Our modern genetics, this V was Viewfield. That was better than an old standard like Stettler. And interestingly, it was from an all banded treatment. Stettler was a little bit better when we had lower yield potential. That's probably by consequence of it being a little bit taller variety. So genetics matter, folks, when if and when you can predict what kind of productivity environment you're going to have. And again, just keep in mind as well, like we have a silty clay research farm just southeast of the airport. It always looks like it's soaking up water like a sponge, but the problem with that is that it's basically unavailable water. So your soil and type and texture matters with respect to how much water it's willing to let go of. So keep that in mind too in terms of tempering expectations based on the precipitation that you've received. The good news, though, is that there are practices, and I think you're all doing it now as it is, in terms of what can increase field water holding capacity. Conservation tillage, no-till, some cover cropping, those sorts of things versus conventional tillage, which just may seem counterintuitive, but it's not. That allows for better water holding capacity. What about seeding depth? Basically, in a lot of different scenarios, including corn or maize, going deeper is actually a little bit better. So you anchors the crop a bit better. But all of that kind of is based on how well you've set yourself up for deep rooting potential, going back to your soil type and texture. And there's a lot of ways you can manipulate that and, plant available nutrients, strategic tillage potentially, or at least minimizing hard pan compaction, all that kind of stuff. Back to Australia, and one thing they're doing, they have super sandy soil, so they've developed wheat genotypes that with a long coleoptile. So these things can root down really deep to chase water. And I think we don't have those kind of soils, but I think these sorts of ideas should be an inspiration to our breeding and genetic enhancement people of coming up with longer term solutions around drought management. And so I hit up a buddy of mine just to wrap up here in terms of what's important to him on his farm in Mossbank, Saskatchewan. And basically Dale says, well, I'm going to budget about $120 an acre. And my first priority in the context of drought management is I want to protect the plants. So I'm not looking to add more stress, which is something we can accidentally do a lot if we're not careful. He reassesses his canola acres and potentially, well, most probably pivots to a more drought tolerant crop. He does use ultra early seeding and he combines it with taller varieties. And he barely complains that we don't have enough taller varieties right now. Nitrogen, pay attention to the salt index. So if you're working with anything like ammonium sulfates and stuff with a higher salt index, that can cause major problems in a drought situation in terms of salinity. So you got to be careful about that. And then scout and be smart about weed control. Make sure you actually need to apply that herbicide. And if you do, avoid the hotter alternatives and maybe stick to more simple basic stuff, MCPA, Authority, your Abidex versus some of these hotter alternatives. And then what about fungicides? Another thing that can cause problems for plants. You don't want to beat the crop to death. So make sure you need that fungicide, but also make sure if you need a fungicide, there's proper soil moisture. If there's not, don't do it. So to me, that's pretty sage advice. A combination of rotational diversity with respect to roots, I think, is helpful. Obviously, it's a no-brainer. The guys with their stripper headers are doing a better job of managing evapotranspiration. That can be key around here. And again, don't overlook the impact of variety. In fact, your variety pamphlets these days are broken down into productivity zones potentially. So try and choose accordingly if you're seeing differences based on productivity zone. And for me, seed treatments would be for abiotic stress, not really for soil-borne fungus or disease pathogens. Keep that in mind. And experiment with depths. We know now that canola can actually go as deep as 1.25 inches, whereas that would have been heresy a few years ago. Hopefully we've proven to you that ultra early is a practice worth trying, as opposed to waiting for rain, and just keep that whole synergy thing in mind because it can pay dividends. And a good example of that is what John Kirkgard did in Australia. These practices up here in isolation only would yield you about 1.6 tons per hectare out there, whereas here when he combines it all to better rotation, better weed control, switching to no-till, earlier seeding, the genetics, that long coleoptile, basically he's tripled his yield. So you can make a big difference if you really focus in on carefully selecting those components. So with that, and apologies, I think I've gone over a little bit. So thanks to the folks that have funded us in the past and the present. And on behalf of my team, thanks for the invitation today.
Great presentation, Brian. That was really good. We got some really good questions out of it too, and we'll get to those questions after we finish Leonard's presentation here. So we'll jump right into it. Our next presenter, Leonard Hingley, is an irrigation specialist for Alberta Agriculture and Irrigation. He will be presenting on water use efficiency and irrigation. So good morning, Leonard, and welcome.
My name's Len Hingley. I'm an irrigation specialist for Alberta Agriculture and Irrigation. Thanks to Matthew and the county for asking me to speak here today. I get to speak to you about water use efficiency and irrigation management in corn. And Matthew gave me the opportunity to choose the crop, and so I decided with corn, knowing how many corn acreages there are in Lethbridge and area, I thought probably the best crop to choose to talk to you about today, given the time constraints I'm on. So without further ado, let's get into the presentation. So first thing I'm going to talk to you today about are water use efficiency. We're going to give you some definitions there. And then we're going to talk to you about drivers, what drives water use efficiency, corn crop characteristics, crop water use, what that looks like for corn. And then we're going to get to a quick review of soil water holding capacity and some of the definitions surrounding that. And then targeted strategies and general strategies to improve our water use efficiency on farm. So first of all, what is water use efficiency? Well, many people call it crop water productivity, but it basically is the ratio of net primary product to evapotranspiration. And so this is kind of the working definition that we're going to work with today. It's water use efficiency is our yield, our actual yield, or grain yield, or marketable yield, over ET, which is our evapotranspiration or crop water use. But that's not the only definition that's out there. I'll share a few of those. You can see here the top definition. If you're a plant physiologist, you know what this is all about. This is about how well my particular crop is going to generate yield given the amount of water I give to it. So for a C3 crop, if I give 600 grams of water, I can yield 1 gram of product. C4 crops are a little bit more efficient. 300 to 400 grams of water will generate 1 gram yield. And then lastly, our CAM plants, 80 grams of water for every gram of yield produced. Of course, we're focusing on corn today, so that's our C4 plant. Our second definitions are TA. TAs are total available. And so what we're looking at there is our available water at the bottom with precipitation and irrigation, and our yield on the top. That's our numerator. Our third definition is our crop water use efficiency. That's yield over precipitation and irrigation. The fourth one I have there is irrigation water use efficiency, and that's our irrigated yield minus our rainfall yield divided by our actual irrigation. And then lastly, our fifth definition would be our ET water use efficiency, which is our irrigated yield minus the rain-fed yield divided by our irrigated ET minus our rain-fed ET. So there's lots of definitions out there. But again, we're going to go back to the one that I first mentioned, which is our yield over crop water use or yield over ET. And so those are our main drivers. So what we want to do is we want to reduce our water use or increase our water use efficiency, which is reduce the amount of water that we apply. We could also affect our yield, so we can increase our yields. And of course, Brian has mentioned many of those things that we can do for that. We can have our early seeding if it's something that will benefit you. We could also push the nutrients, soil. We could add soil amendments. We could add compost. We could change our seeding rates and our seeding dates. So those are the things we could do with yield. But today we're just going to focus on that crop water use part. How can I manage the water that I apply to generate the same yield without applying as much water? So corn, again, it's a C4 crop. I mentioned that, what that means. Corn is a warm season crop. Both warm soils are necessary as well as high temperatures. And for those of you that grow corn, you know that if it's a cool season, I'm certainly not going to generate as much yield. Corn growth increases at increasing rates as maximum daily temperatures increase from 10 to 30 degrees C and then at decreasing rates to 50 degrees C. In Lethbridge, Alberta corn requires 425 to 500 millimeters of water when grown under optimal conditions. In some of our literature, we have it around 500 to 550. I did some work recently, and we have some ET data from the last 25 years in Lethbridge, and it's probably closer to 425 to 500 is what we're looking at for an average amount of water applied. So before I can give you some strategies on how to save water, first we must know how corn uses water. And we'll get into that. So every couple of years, for the last 25 years, I guess, we have put out what's called a Bowen ratio in producer's field to look at what our crop water use looks like in southern Alberta. And local conditions are critical for developing these crop water use curves. So we go out, choose a particular crop to look at for a 2-year cycle, and then we put this apparatus out in the field. And what it basically tells us is the Bowen ratio. The Bowen ratio is sensible heat flux to latent heat flux. It's just that ratio. So H is our sensible heat, which is just a change in temperature from 1 degree to the next. And LE, which is our latent heat flux, is a change in phase. So we have our next equation there is Rn minus G, which is our net radiation minus our storage term, which is our soil storage term. And that equals our H, which is our sensible heat flux plus our latent heat flux. So basically what we're looking for is the last equation there. So what we're looking for is our ETC or ET crop. We want to know what our crop water use is. And each crop has a different crop water use signature. And this is what silage corn looks like in southern Alberta. As you can see here, we have our, on the x-axis, we have our months, May, June, July, August, and then we also have our growth stages of our particular crop here. In this case, it's silage corn. And then our y-axis, we have daily water use in millimeters. And again, like I said, it uses about 425 to 500 millimeters. And as you can see, there's a particular signature. Each crop has its own signature of crop water use. Our particular signature for corn is peaks in July. So our reproductive phase is using the most water. And our vegetative phase, as you can see here on the back side here, just after seeding, it uses less water. And of course, as our crop senesces, it's the same thing. Most crops have a very similar bell curve or signature, but this is exactly what silage corn looks like in southern Alberta. So before I move on to our key strategies, I want to talk about soil water storage. And if you look at this, it's basically a bucket of our soil profile. The top is our temporary storage. So if we're under saturation, so just think about that soil parcel. And if it's full of water, just full of water, so we don't have any air anymore, all it is mineral soil and water, it's at saturation. Now, once we allow that to drain for 48 hours, so that gravitational forces pull that water out, so that gravitational water is lost, and then we're at field capacity, which is the light blue in the middle. So at field capacity, we're at 100% of available. So that water that's available to the plant is more available above 50% than it is below 50%. So our crops are not working as hard. They don't work hard to remove that water, that available water above 50%. But once we drop below 50% of available, it's still available to the plant, but the plant has to work a little bit harder to pull that water out. And in essence, what it's doing is stressing the plant. So we want to maintain that soil water profile above 50%. Then anything below that, so we have that permanent wilting point, that's unavailable to the plant. So the plant cannot extract that water from the soil. So that's just a quick review before we get into our strategies here. So now that we knew how much our corn uses, and now we can look at what kind of strategies we can employ to improve our water use efficiency while minimizing our yield losses. Now, this graphic came from Nebraska. It's our maximum allowed depletion to maintain maximum ET. So on our x-axis, we have our maximum ET in inches per day. That's the bottom line that you'll see there. So the 0.08 all the way to 0.39. And then I've added above that those values in millimeters. So we have 2 millimeters on the left and on the right, 9.75. On the y-axis, we have percent depletion. So at the top is 90% depletion. So what that 90% means, it doesn't mean, it means it's about 10% of available, okay? And at the bottom, it's a 10% depletion, which would be 90% of available. And then we have two different crop mix signatures. So the top crop mix is corn, sorghum, soybeans, sugar beets. That's how they respond to ET. And then below that is that dotted line of alfalfa, beans, sunflowers, and wheat. So we're going to look at this top line as we're focused on corn. So the one thing that this tells us is that early in the growing season, we can have very little water in our soil profile and not hit water stress for a crop. So that is the time we want to target less water on our particular crop. If we're trying to save water in a drought-like situation, we want to improve our water use efficiency. That is the time when we target. So that's what I'm going to look at through the rest of this presentation. So one thing we can do in order to do this is use regulated deficit irrigation. And this was first coined by Chalmers in 1981. This irrigation strategy reduces water applications during periods of water stress. And it certainly helps in minimizing those yield losses that we'll see. So this next slide, on our x-axis, again, days since corn emergence. So we have time, and then we have our yield susceptibility on our y-axis. So from 0 to 60% yield susceptibility. So if we look at this, this is a growth curve for corn, and we look at our peak water use, which coincides to our peak growth period, and also it's our peak yield susceptibility period, which is tassel and silk, which is our, like I said, not the vegetative period, but the reproductive period of our growth. So we don't want to short a crop there, but if we look down on the left there, we look at days since corn emergence. So we have 25 days since corn emergence. So our corn is growing, but we don't see much of a yield susceptibility. So that's kind of where we want to target. Here's some other work that was done by Meyer in 1993 on drought sensitivity. Again, showing the same thing during silking and blistering. We finding drought sensitivity in our corn. So we certainly don't want to short a crop there. So this is some work done by Wang in 2023 and their group. And what they did was they had a deficit irrigation treatment, a number of them actually, and then a regulated deficit irrigation treatment. So I think they had 10 treatments in all. And what they did was they combined the results of that, and then they synthesized that into a strategy that can be employed by producers in that area. The reason I chose this one, it was in a semi-arid region, China, and it was similar to our climate here. So I thought it would be something that can maybe translate a little bit of their knowledge here. So at the beginning, you can see on the left-hand side where we see sowing, what they did was they irrigated 30 millimeters of irrigation to increase their soil water storage. That's the SWS term there. And then they didn't apply any irrigation from VE, so that emergence, until V6, okay? Unless they hit a lower limit of soil water holding capacity or soil water content, 60% field capacity. So if it dropped below 60% field capacity, they would top it up. And then after that point, from V6 to tasseling, we saw 88% full irrigation. And then from tasseling to R3, R3 is the milk stage, for those of you that don't know. We would apply 100% of ET replacement. So that would be our full irrigation treatment right there. And then from R3 to R6, so milk to maturity, we would see 85% of ET replacement. So that was their suggestion. Let's talk about their management of this particular trial. I'll talk about the highlights here. So what they wanted to do was top up that 0 to 20 centimeters after sowing to increase that soil water storage. And then irrigation should be withheld between seedling and V10 stages under normal precipitation conditions. And so they wanted to reduce their ET to about 30%, 36% per. And by doing that, certainly were more efficient when they applied that. So what they want to do is make T big, right? You want to increase your T, your transpiration, so your plants are producing well, but you want to eliminate that E. And so at the beginning of the growing season, what do we see out in the field? When I look at the field, I don't see much green. I see a lot of brown. So if my brown is wet, if all the soil is wet, then we're losing a lot to evaporation. So I want to reduce the amount of evaporation I see in the growing season. So that's why we reduce it at the beginning, or in part, why we reduce it. So number 3 here, if the field receives less than average rainfall at the first irrigation, we can advance that to the 6th leaf stage. So you can irrigate early if necessary. And then less than full irrigation should be applied between V6 and VT. So this is just a recapitulation of what I showed you before. So I won't go through that too much further. Now, Nebraska had a water miser, BMP strategy, and it's similar. They noted for years of the work that they did back in the 80s and 90s that same kind of results that we saw with the work in China was done here. And so what they found is if irrigation is delayed until about 2 weeks before tassel, emergence of corn, the soil water depletion exceeds 70% of the active root zone. So that's what they wanted to do, delay irrigation until 2 weeks before tassel. And then once the crop reached that reproductive growth stage, the plant available soil water is maintained in a range between fill capacity and 40% of depletion. So 40% of depletion is 60% of available. And they didn't mention that 70% of depletion then would be 30% of available. And then on the right-hand side there, after the hard dose stage, the soil is allowed to dry down to 60% depletion. So what do we do with management here? This is kind of a synopsis of what they did. Again, upper meter of that profile should be at or near field capacity in the early part of the growing season. One caution that they mentioned in the research was that the irrigation must start soon enough to avoid excess stress during the pollination period. So sometimes they would delay that, and so you have to watch fairly closely where you are in your field for that growth period. You don't want to miss that window, and you want to make sure that you have enough water going into those sensitive or reproductive stages of growth. The research also found that water savings of more than 4 inches, or about 30%, could be achieved without a significant yield reduction if water was withheld only during the vegetative period, and then full irrigation was applied afterwards. So during the spring and early summers with above normal precipitation, they did not note any savings. And that should be expected as we apply water later on in the season. We're only mirroring what's going on in the field, right? So if I should have been applying water early on because I didn't get any water, then I'm going to notice a bit of a bump because of that. But if I had normal precipitation come in, I'm not going to see those same types of savings. All right, so a combination of the results. What we saw was for both studies that targeting early irrigation to top up soil moisture status was critical. Minimizing irrigation events during the vegetative stages was critical also, and then also maintaining full irrigation through the reproductive stages were common in both studies. So lastly, let's get into our general management strategies, pardon me. And this is something that Brian kind of mentioned, touched on a few of them, so I won't go into them in great detail, but I will mention them. Civil management, Dr. Philip Harder, he is a research director for crop mystic technologies, but he did some work through the U of S on dryland farms in Saskatchewan, and he noted that by increasing cover by 10%, we could reduce soil evaporation by 5%. And though this work is targeting dryland farms, the same principle applies for irrigated farms. The more water irrigators can retain during the winter months, the less water they need to apply in the summer and the spring. Another one is minimum or no-till. Direct seeding increases crop residues, improving your soil health by increasing your tilth and organic matter. This improved soil health can increase the surface residues, which conserves soil moisture, leading to higher yield potentials. It's much like having natural mulch on your field as opposed to black mulch that many people apply. So if you have that natural mulch, what you're doing is just protecting that soil moisture from being released to the atmosphere, right? And then lastly, when soils are moist, you can lose from 1/2 inch to 1 inch of soil moisture for every tillage pass. Another thing that we can focus on, I think again, Brian mentioned this, rotations. A pea crop with its lower water use and shallow rooting depth generally leaves moisture below 60 centimeters. So if I have that extra moisture, don't want to apply extra moisture, well, I can seed a crop like corn that roots down to 1.2 meters the following year, and it can extract that bottom 60 centimeters that wasn't extracted by the peas the previous year. So that's something you could look at. Hybrid varieties, some new hybrids have proven to be more water use efficient than others. How much work is done on that, but I had noted some. It's maybe not overly conclusive. I think it varies from year to year, but it's something worth looking into. And then lastly, adopting more efficient irrigation methods. Not just SDI. SDI is one of them, subsurface drip irrigation. You could also adapt PMDI or precision mobile drip irrigation, those long hoses that we pull behind our pivot. You could also LIPA, which is low energy precision application, which we put our drops about 18 inches above the soil surface and just apply water that way. And that just improves our efficiencies, okay? So with SDI, we're about 98% efficient because we do apply it directly to the root zone. We can really push the nutrients. So the one great benefit of having SDI, especially for water use efficiency, is that, again, we're 98% efficient, but we can also push those nutrients and really push the yields, okay? And then it also limits wetting of the vegetation and soil surfaces, reducing weed and disease pressures. And in terms of savings, SDI assumes about 25% water savings over CP. So that's center pivot irrigation, and that's a MESA system. So that's a mid application. So basically, if you look across an irrigated area and you're looking at a pivot, it's probably going to be a MESA system, mid elevation spray application. And then lastly, it irrigates a larger area. So if I have a quarter section of 160 acres, I can actually irrigate that whole 160 without missing the corners. And so for a brief review here, so we went through some regulated deficit irrigation strategies in China and Nebraska. And again, they mentioned target irrigations early, top up soil moisture, minimize irrigation bench during the vegetative periods, and then maintain full irrigation through your reproductive stages of growth. And then our general strategies to improve on farm, water use efficiency, so subsurface drip. So you want to make sure you have an efficient irrigation system. Hybrid varieties could be a benefit to you. Stubble management, no-till or mulch. And with that, we'll answer any questions if you have.
Thanks, Len. Great presentation. Like Len said, if anybody has any questions, please throw them in the Q&A chat box, or you can raise your hand and we can call upon you that way too. I see, let's see here. I see Brian. Yeah, I started answering a few questions already, so that's good. Um, I do see we got one question here that wasn't answered yet. So, and I believe this one was for you, Brian. So, any observations on weed control? When you plant early, do you get ahead of them or do you have to spray more to catch early and late flushes?
Yeah, that's that's a good question. And we've looked at that. We had a PhD student who I quite nice coincidence worked for New Farm, now Dr. Graham Collier. So what we did, you think about ultra early and think about the benefits if you're into or winter wheat production. That's kind of what we're trying to get out of an ultra early system as well. So with winter wheat, we know we can get much better weed competitive ability from that crop. So fewer herbicide inputs are possible. The other upside with ultra early is obviously if you're going February 9th and planting, there's probably no weeds there to control. So the utility or the need for a glyphosate sole application or glyphosate mix is not needed. And that helps to slow the evolution of resistance to glyphosate on that field. What you can do though, and work that Graham did showed quite nicely, is that if you plan ahead and do a soil residual herbicide, like a pyroxasulfone, with tank mix of flumioxazin, I believe it's Fierce as a tank mix. That's really good planning. That'll be good. But generally, our experience too was, if you do adopt ultra early, that one in crop application generally was sufficient to manage weed competition anyway. But if you really want to get keen on it, think about um, soil residual herbicides in the fall. Now, just if you're using targeting durum as the crop, just be careful on what you select because it can be sensitive um, to some of that. So just do your homework that way.
And then going pivoting from the weeds there, Brian, like I had a question on that too. So could changes in seeding timing influence insect feeding patterns on crops? Did you guys notice anything like that, or was it pretty similar across?
Did you say insect feeding?
Yeah, yeah.
Yeah. So, I mean, it's a good question. And the answer, like we've just done it with wheat and durum, right? So I would say that, you know, again, back to winter wheat, you might be disrupting synchronization patterns with conventional spring wheat life cycles if you all of a sudden upend that by going with an ultra early system. It kind of lends itself or leads into the question of seed treatments too, which you think about intuitively. You think, okay, if I'm going to use the stress shield neonic seed treatment, that means I'm trying to manage some soil-borne insects like wireworms or something. And the experience from us with all the work that we did on winter wheat was that it wasn't about, honestly, it wasn't about controlling the soil-borne pathogens or soil-borne insects. What we're seeing and what we know, and what we also showed was that if you apply a dual seed treatment to wheat or cereals, you'll actually change the metabolic pathways such that that plant will become more resistant to abiotic stress, which we assumed we needed going into cold soils. But we've seen great advantages in winter wheat, but we just wrapped up a study, although it was just at Lethbridge, where if there was a place where you probably didn't have to obsess about seed treatments, it's probably Lethbridge. But we didn't seem to see the same advantages there that we observed with a prairie-wide study in winter wheat when it comes to seed treatments.
Okay. And then for you, Len, a question I had, you talked a little bit about the subsurface drip irrigation, and I know we had a presenter I believe it was last year, the year before, from the Lethbridge College on it. Are you seeing a lot of uptake with the subsurface drip irrigation, especially like with regards to corn and stuff, or is it still a lot more center pivots?
Yeah, there is a lot more people still focused on center pivot irrigation. There's this few challenges with SDI, but I think those that have adopted SDI really enjoy it and have actually expanded acres. The one benefit of it, like I said, is that you can really push yields because you can directly impact growth throughout the growing season by adding your nutrients to the roots themselves, which is a real benefit, especially for corn, right? You can really push yields with that. There's challenges to SDI, but like I said, those producers that have it and that I've talked to have not been dismissive of it. Let's put it that way. They've enjoyed it, and they probably would add more acres if they had the opportunity.
Yeah. Are you with the SDI, would you see, I don't think it would work with really well with potatoes and sugar beets with the amount of tilling and whatnot on the land, but would you see that being utilized for other crops in the area too, or am I mistaken on that too?
I haven't seen it. I haven't seen potatoes under SDI. No, I
Yep.
don't know about that. Certainly on cereals and some of the crops that we see up here and the Newell County, we see it a little bit, but not a lot. It can be a niche thing. Again, some guys say that, oh, okay, well, it's not really helping me with germination. That could be an issue. But if it's applied properly, it's installed properly, if you maintain it properly, because there are a lot of maintenance issues with it, and management doesn't look like it does with a pivot. Like with a pivot, I can turn it on and let it go, right?
Yeah.
With SDI management, it requires a lot more hands-on, a lot more time.
That's good to know. Another question for you, Len, from Scott. Was it 1/2 inch to 1 inch of water loss per tillage pass?
Yeah,
And
that's correct.
okay,
Yeah.
and then the other question I guess is so shallow would be less, but the deeper more.
Correct. Yeah.
Then is there any other questions that anybody has before we? Everybody's quiet today. I guess I have one more question for you guys. What are the most common mistakes you see that producers make when trying to implement drought mitigation strategies? Are there some mistakes that you guys noticed, or are farmers pretty diligent and so on and so forth?
I mean, I think it's so easy for to be a bit of an armchair critic, but I can empathize with the fact that there's a lot going on a farm, both business and management side of things. So I think it can be real easy to overlook one of two things. One is not properly planning your input strategy and your return on investment strategy around what you anticipate to be your yield. So there's that business side of thing, and that's why I was bugging Dale about to give me a number on his inputs, and I figured it would be about $100 an acre, and he was like, well, it'll be maybe 120. And so what he sees too is that people aren't sort of moving the bar of that to properly relate to what they're going to expect for yield. So that's one. And then the other thing is, just things that these things that you do over and over again. And you kind of overlook it, like that whole salt index thing. Like if you're not paying attention to that, all of a sudden it'll really come and bite you, particularly in those dry cycles. So I think a couple things like that, and just trying not to beat up that plant with too much. Like every time we put, and it's poison, right? Every time we poison that plant, we shouldn't expect it to just jump up and be all excited, like it could eventually get a knockout punch from too much herbicide, too much fungicide based on, the conditions.
The one thing I would add is I think early planning. I think that's the one thing that's critical, especially from an irrigation management piece. If you go into the season and I'm like, okay, here's my crop rotation, this is what it looks like. And I know I'm seeding the corn, I'm seeding peas, I'm seeding whatever, lentils, whatever you're seeding, right? And I know how much water each one of those is going to use throughout the growing season. And then, okay, what if I'm hit with a drought? What if I'm hit with limited allocation? How am I gonna break that up? What is those allocations going to go to? Am I going to prioritize my peas or am I going to prioritize my corn? What am I going to do, right? And just have a plan moving forward. Because if you have a plan moving in and you know, okay, then I'm just going to implement my plan instead of kind of just flying by the seat of my pants, right? So I think it's critical to make sure that you get a plan in place early and know what you want to do. Because you don't know when the drought's going to hit. You don't know when your allocation is going to be reduced. So
that's a good remark, especially with what we've been seeing the last 2 years, and especially in this area. You guys both had really good remarks there, so I appreciate that. I got one more question. Somebody just put it on here. So, did you have have a chance to verify with GDD and crop phenology? Oh my goodness, it's the end of that. It's a Monday. Phenology stage with ultra seed or ultra early seeding, and did they show any correlation with right amount of accumulated GDD?
Well, we wouldn't be interested in that, to be honest. I think what we're more interested in is verifying that we're shifting the critical growth period out of July. And to me, that's the big one. And in a perfect world, we would not just shift it out of the critical. We would not just shift it out of July, but we would also think of it as a rubber band, also get a benefit of it expanding. But we haven't observed that yet. We have, though, been able to completely shift it out of July, which is a real big deal, to be honest. And that, I mean, if someone told me 10, 20 years ago that they harvested their durum August 1st, I would think that the kernels looked like rice, you know. But you saw the example there, they didn't. And so, you know, I think the best way to two things with ultra early seeding is, like, we've got a lot of experiences now on the research side, like I said, 50 plus site years, but we've also got producers now in both Alberta and Saskatchewan doing it and having success with it. So yeah, that's been a real positive project personally, because it seems to have caught on, and it's helping.
Awesome. Well, we'll get into closing remarks here. So, I'd like to extend my thanks to everybody who joined us today. And a special thank you to Brian and Leonard for their informative presentations. I really appreciate you guys taking the time out of your days to come and present to us here today. And please join us again next Monday, February 3rd at 11 o'clock a.m. for our next session featuring presentations on soil amendments by Jeff Chanel and soil health indicators by Emily Zavala. Thanks again, everyone, and we will see you again next time.